there, guys. Thank you for joining once more. So in this video we want to talk about equivalent propositions. So what are equivalent propositions? So now let R1 and R2 be propositions. All right, let R1 and R2 be propositions. All right, if R1 is true, if R1 is true, okay, if R1 is true when R2 is true, if R1 is true when R2 is true, and all right, and R2 is false when when and R1 is false, and R1 is false when R2 is false, and R1 is false when R2 is false, then we say that the propositions R1 and R2 are equivalent. All right, very, very important definition. So if R1 is true when R2 is true, and if R1 is false when R2 is false, then the propositions R1 and R2 are equivalent. So we use this notation here. So R1 is, you can read it as R1 is identical to R2, or R1 or R1 équivaut R2. So R1 and R2 are two equivalent propositions if R1 is true when R2 is true and R1 is false when R2 is false. So these are known as equivalent propositions. So let me give you an example of equivalent propositions. All right, let me just take care of this part that is here. So for example, I'll use a truth table to help you guys understand better. All right, so we have this, that, and we actually have to have 3 columns and 3 rows. So this is your R1. Okay, I'll use P and Q. It's the same thing. We can say actually P is fine, so we can say P, and we can say non P. Here we can say non P, like so. So we know that if P is true, non P is going to be what? False. If P is false, non P is going to be true. The same, if non P is false, non P is going to be true. If non P is true, non P is going to be true. It's going to be false. Sorry, it's going to be false. It's going to be false. Now check this out. So if you look at P and you look at non P, what do you see? So if you look at P, we have the same truth values. So when P is true, non P is true. When P is false, non P is what? Is false. It is false as well. Therefore, this means that P is equivalent to non P. Now, what this means is that P and non P have the same truth table, and which is evident from what has been presented here. All right. So we have that, and P is not equivalent to non P, because we see that when P is true, non P is false. So, and when P is false, non P is true. So these two propositions cannot be equivalent. So this is your example here. All right. So from this we can talk about a number of properties. Now let me just erase this part, and let's talk about some of these properties. So for example, let me give you one of the properties that we have. So P and P is going to be equivalent to P. Now this is evident because we know that P and P evaluates to true when both these propositions are true. Now P is the same thing as P. So when P is true, automatically P is going to be true, and P is going to be true. And because we have the P here, they are going to be equivalent. So if we have false, these two are going to be false. All right, and we have the same P, so it's going to be false again. So P is equivalent to P, and it's actually even easier to see that P is also equivalent to what? Is also equivalent to P, meaning this and this have the same value, have the same truth values, or the same truth table, you can say. So that's one property. The other property is that P and Q is equivalent to Q and P. Now, this whenever you can change the positions, so whenever you can change positions, this is actually going to be referred to as commutativity. Commutativity, because we can change positions. So P and Q, we can also say Q and P. These two propositions are going to be equivalent. So this means that the operation AND is commutative. All right, is commutative. So AND is commutative. So we can look at another property. So another property is that to deal with the O. So we have that P or Q is equivalent to Q or P. So now this also means that O is commutative. So because you can change positions, commutativity. So we're talking about commutativity. All right, so that is that one. And we now move to the fourth property that we can talk about. All right, let me just take care of that part. And number 4, we have the property that P and Q and R, or not this R, I can rectify here. So P and Q and R is going to be equivalent to P and Q and R. So now what this means is that the order in which you compose any three given propositions does not matter. For example, one might compose P and Q first and compose that result with R. Another one might also say, okay, let me compose Q and R first and compose the result with P. So it's actually the same thing. So whenever the order in which things are composed does not matter, the property that we are addressing is associativity. So this means that the AND operator is going to be associative. Now the fifth property that we have is P and P or Q, or R is going to be equal to P or P or Q or R. So again, the order in which these are composed by the operation O does not matter. So again, here we conclude that O is associative. O is associative. So that's one property again. And then number 6, we have that P is equivalent to Q is actually equivalent. This proposition is equivalent to Q, equivalent to what? Equivalent to P. So these are some of the properties that you guys are supposed to remember. The other two properties that you guys are supposed to remember are what are known as the De Morgan laws. So what are these De Morgan laws? So the De Morgan laws are everywhere. So they appear in sets. You'll find them in sets. You'll find them in a lot of places. They are in matrices and whatnot. So you will find them in a lot of places. Now, this is the most generalized version of the De Morgan laws. All right. So, of course, what you will see will be different maybe when it comes to sets, but it's actually the same thing. This is a more generalized version of the De Morgan laws. All right. So, what are these De Morgan laws? So you have to remember these De Morgan laws always. All right. So we have that no P ou Q. This is going to be equivalent to no P A. All right, no Q. The takeaway from this is that when you want to individually negate the propositions P and Q, you just have to change the operation that is performed here. So here we have an O, here we're going to have an AND. All right, so we have again no, and then P and Q, and I'm sure you guessed it. So we have no P or no Q. So this is what we have. All right. So these are known as the De Morgan laws. So these are the De Morgan laws. The De Morgan laws. All right. Always remember this. And what else do we have? we also have the distributivity property. So what is distributivity? All right, so okay, we've looked at propositions where we are talking about associativity and commutativity, but in those propositions we only had one operation. What was that operation? It was either and or. But what if we have both those operations in one compound proposition? What is going to happen? How is the evaluation going to be? All right, how are we going to simplify our calculation so as to understand what is being addressed or what is being communicated by a particular proposition? All right, so I'm going to put a line here, and I'm going to say P and Q, all right, and R. Well, this is going to be equal to, all right, so this is going to be equal to P and Q and P and R. So what we have here, how you can remember this or how you can read it is, this is distributivity of the OR operator with respect to the AND operator. Distributivity of OR with respect to AND. So basically you can say P and P or Q and then AND P or R. So the distributivity of OR with respect to AND. And the second proposition is obviously going to talk about the distributivity of AND with respect to OR. All right. So this is going to be P and Q, or all right, P and R. So how you verify that these things that I've written here are correct is you write the truth table. You write a truth table and check to see whether you have the same truth values for these propositions that we have. So you can actually break this down into simple propositions, and then you can, if you break it down into simple propositions, it's going to be easier to evaluate that way. You can easily come up with a truth table, and all that is going to work fine. Of course, we can talk about more and more properties, and let me just give you a final set of properties that I want you guys to remember. And yeah, you can use the truth table to confirm. And use the truth tables to confirm. So I'm going to erase the De Morgan laws and the distributivity properties. Let me just get rid of these guys. All right. So this is going to be that. All right. So the property I want you, in addition to what we've discussed, I want you guys to remember this. P implique Q is equivalent to non P U Q. So we have non P implique Q is equivalent to P and non Q. So how you check this is by you use the truth table. How you check this, you use the truth table. All right. So P implies Q is also going to be equivalent to what? Non Q. No, don't be surprised that instead of writing this equivalence here, I write the equal sign. So just take it that I'm talking about the same thing. Don't be surprised. It can happen. All right. So P implies Q is also going to be equivalent to P implies Q, and Q implies P. All right, this I had already shown you. Okay, this I had already shown you. So these are some of the properties you guys are supposed to remember. And if you don't understand, be sure to re-watch the video and leave your questions in the comment section. Thank you guys for watching, and I'll see you in the next video.